This is a short recorded lecture on confirmatory factor analysis. So to pick up on where we left off talking about structural equation modeling, we're going to talk in this lecture about confirmatory factor analysis, or CFA, which is a subset of structural equation modeling, or SEM. So we talked about this idea that in structural equation modeling, the really powerful thing about the approach is the pre-specification of a model and then the fit of that model to the data that is on hand to ask the question of how the model fits the data. So in CFA, it's exactly the same thing, only the specific model that we are specifying is one that fits a number of indicators to a hypothesized underlying latent variable structure. And so when I say indicators in this context, most often what we're talking about is a number of scale items. So for some given measurement instrument or scale, the CFA allows us to ask how a particular structure, an underlying structure, fits the data. You guys remember that we talked about this idea that indicators can either be the cause of a reflexive or the cause of a latent variable, and that's called a formative model. So, and in that case, the indicators or the items are called cause indicators because they cause the latent variable, and the arrows point from the indicators to the latent variable. That's pretty rare in confirmatory factor analysis because, according to the common factor model, what we are most often specifying is a reflexive model that says the latent variables, the underlying latent variables, are the cause of the indicators. In which case, the indicators are called effect indicators because they're effects, and the arrows point from the latent variable to the scale items or to the indicators. We saw this figure when we had our SEM discussion. So this larger figure is a structural equation model. But most, if not all, structural equation models contain a CFA within them, which is called the measurement model, because the measurement model does correspond to the case where we're just testing the fit of a number of indicators with some hypothesized latent variable structure. Measurement model is synonymous with confirmatory factor analysis. So what we do then is, as in any structural equation model, is that it's very important to specify the model. And what specification means is just sitting down. In fact, specification may mean drawing the model, right? Drawing the arrows, drawing the squares, drawing the circles, making a very explicit statements about what that model looks like, the number of latent variables, the number of observed variables, the relationships between the latents and the observed, the relationships among the latents if you model them, if the specification of the error or residual variables on the observed variables. The couple of things I sort of skimmed over here are that let me say this. So you have to specify the variances of all the observed variables, which is the same thing as saying how much of the variance in the observed variable is accounted for by the latent. Everything that's left over that isn't accounted for by the latent has to be modeled as the residual variance of the observed variables. You can model covariances among residuals, which is saying that the error terms of the observed variables are themselves related or correlated. It's a pretty subtle thing to specify, and in fact, we generally don't want that to be the case. We want the errors in the observed variables, what's left over after the latent variable has accounted for what it can, to be independent of each other. But when that might not be the case, you can certainly model it. So that's what we do. We sit down and we draw out the model, what we want to estimate, or what we think the model looks like. And then we say which specific parts of this model are going to be estimated from the data. So we call those free parameters, or those are the parameter estimates that are going to come out of the model. You guys may remember this idea of a parameter, right? A parameter is a population statistic. So sample statistics are called statistics, but what we're generally doing with our sample data is trying to estimate these population values, and those population values that we estimate from the data are called parameters. So in these models, in a CFA model, we have to say what parameters, what population parameters are we trying to estimate, and we call those our parameter estimates. They are free to vary in our data, or free to be estimated in the data. And generally, in a CFA, these are going to be the loadings of every item with the latent variable that it loads to, the covariances among the latent variables. If you model them, it's perfectly reasonable to not model them. Remember, we got to model the error variance of every single observed variable. And then, because in a CFA, these are endogenous variables, these are the latent variables in a CFA are considered endogenous. They're inside the model. And so we have to model the variance of the latent variable. And so however many latent variables you have to model one variance parameter estimate for each latent. So when you sit down and draw your model, and you then think through what are all of the estimates that I have to make in this model based, from the data. And then the next step is to say, well, how much information do I have to make those estimates? And in SEM or CFA, the information that you have is the variance covariance matrix among the observed variables. And that's why a few weeks ago, when we first started talking about some of these measurement statistics, we talked a lot about what a variance covariance matrix looks like and what the covariance is, what it represents. Because these are correlational techniques. And so the information that goes into the model are the covariances, which remember are just unstandardized correlations among every pair of variables. And that's what's in the specific intersections of the variables with each other in the variance covariance matrix. And then remember, on the diagonal of the variance covariance matrix is just the variance of each individual item. So that's all the information we're going to feed into the model in order to let the model make the parameter estimates that we need it to. So those are called the sample moments. And there is a complex and technical explanation for why those are called moments. And in fact, the software that I talked about in class that used to be free to do structural equation modeling and confirmatory factor analysis was called AMOS, A-M-O-S, and that stood for Analysis of Moment Structures. And so just the thing to remember without the technical explanation is that the sample moments are the information available in the data, and that basically that is the number of elements in the variance covariance matrix. And you get that by multiplying the number of observed variables by the number of observed variables plus 1. So if you let P indicate number of observed variables, that's P times P plus 1, and then divide that whole thing by 2. So I know that seems a little complicated. We're going to practice it. So let's practice on this hypothesized model. So this model, which I just drew it by hand, this doesn't correspond to anything real, but this is a model that seems reasonable. Here's a model with 6 items, indicators. So those are the boxes. And we're hypothesizing the model that we're fitting to this data is to say that the underlying structure of these items or indicators is that there are 2 latent variables, and the latent variables are the causes of the indicators. So this is a reflexive model. And then down at the bottom, you can see there's an arrow. It should have a double head on it, but basically we're saying here, these 2 latent variables themselves we're going to allow them to be correlated. We're going to estimate the covariance between the latent variables freely. So let's count up first the number of parameter estimates that we're going to make. We have to estimate the covariance between the latents, so that's 1. We have to estimate the variance of the latents, so that's 2. We have to estimate the the error variances of all the observed variables. So there's 6 of them. So we're at 9 now. And then you might think that we have another 6 things. We have to estimate the item to latent variable loadings represented by all of the arrows. So you might think we're at 9 plus 6, which is 15. But in these models, there's always one path estimate or item loading estimate that has to be fixed per latent variable. So that's represented by those 2 red asterisks. The reason for that is because we have to set a scale for the latent variable. And also there's a technical explanation for this, but it's just to say that latent variables are scale free, right? They're hypothesized entities, but we're sort of hypothesizing them into existence. And so they don't actually have an underlying scale, like this latent variable goes from 0 to 100. So what we have to do is use one of our free to vary parameter estimates for every latent variable and fix it to, and the common thing to do is to fix it to 1. So we got to 9 plus 6. I said, well, we think there's going to be 15, but then we're going to subtract out one loading, one beta coefficient from each latent variable. So that gets us to 13. You'll notice in this model that I was lazy and didn't draw the circles that correspond to the error variances at the top. I just put the black arrow pointing in at the indicator, which we said is also kind of customary in these models. So that's how you count up the parameters that are going to be estimated from a given model. This would be totally customary, right? It would be really strange to say item 1, which we'll say is represented on the far left of the screen, so the first box on the left, to say that item 1, we're going to hypothesize that it's caused by both the first latent variable as well as the second latent variable, in which case we would have another single-headed arrow running from the latent variable on the right all the way over to the first indicator on the left. You could do that. You can do that. There's no reason why you wouldn't do that or couldn't have a hypothesized model where that was the case. But remember, in a confirmatory model, what we're generally trying to do is scale validation, right? I'm trying to sort of think about what the underlying structure of my scale is. And it's not great to have an item which can't be completely explained by a single underlying latent variable. And this has to do with some of the stuff we talked about in exploratory factor analytic modeling, which is we're looking for simple structure, right? So you might have hypothesized this model on the basis of your EFA, in which case, right, what you're trying to then say is, given what I think is happening in my EFA, how well does this particular 2 latent variable model fit the data? Okay, so we said there's 13 parameter estimates to be made in this model. So the next thing we would want to do is to calculate the sample moments. I'm going to go back one. So we have 6 items here, 6 observed variables. So remember, the sample moments is equal to the number of observed variables that you have times the number of observed variables that you have minus 1. So 6 times 5 is 30 divided by 2. So we have 15 sample moments here, which is, I'll just reiterate it again because it's important. 15 is the number of unique elements in the variance-covariance matrix. So it's the intersection, it's the covariance of item 1 with item 2, item 1 with item 3, 1 with 4, 1 with 5, 1 with 6, and so on. All of those unique entries which represent the covariances among the observed variables. And then on the diagonal is the unique variance of each indicator or item on its own. And the reason we do all that work of counting and calculating and thinking about the elements in the variance-covariance matrix is because we can then figure out how many degrees of freedom our model has. And so we have, it's sample moments minus parameter estimates. So we have 15 sample moments and 13 parameter estimates. So we have 2 degrees of freedom. The take home here is just that you must have a positive number of degrees of freedom, right? You must be trying to estimate fewer things from your data than your data sort of are capable of yielding to you, right? The sample moments are all the information available in the data. So you can't build a model that asks a question that's sort of more complicated than your data can answer. And this has to do with the issue of model identification. So just identified models, what you want is an over-identified model, a model which has more information than it does estimates. It's super useful to put this skill into place when you're reading papers, SEM or CFA papers, because you can look at how many degrees of freedom their model had. You can always look at a figure and count up, how many parameter estimates they had, and you can just on the back of a napkin do the calculation of how many sample moments they had as a quick check on whether or not the model seems tenable and if they sort of look like they knew what they were doing. And we'll look at a couple of examples of that, or one example of that at the end of this lecture. So before a model is estimated, so when you're just sort of thinking about a hypothesized model structure, and this is almost exactly the same as the fake one that I made, I just wanted to show you guys the notation that's commonly associated with the structural equation models or confirmatory factor analytic models. These are the parameters that are going to be estimated. So you can see that there's a psi. The psi is the covariance between the two latent variables. The latent variables, really their variances are represented as an eta. Each path coefficient, or the item to latent loading, is represented with a lambda. And then the error variances are represented with an epsilon. So just so you know, these are the parameter estimates that are going to be made from this model. And if you want to take a second to count up how many parameter estimates are in this model, it would be pretty easy to do, right? There's one psi, two etas. There's the number of indicator lambdas minus the number of latent variables, right? So in this case, because we're scaling one of them, so it might look like there's 3, 4, 5, 6, 7, 8 path coefficients to estimate, but there's really only 6. But there are 8 epsilons to estimate in this model. So it gets kind of easy to think about what parameters are going to be estimated. Okay, so once you've specified the model and you estimate it, so first is specification, then is estimation, the model will yield all of the estimates that you've asked for. And we talked about this before, that there's this notion that sometimes the estimates themselves, right, all of those actual values that are estimated from the data, the parameter estimates, are not as important as an overall assessment of whether or not the model fits. And so those values, they're generally called fit statistics, are referred to as generally the goodness of fit, or the fit statistics. And what it's actually saying is, you had your input, which is the sample variance covariance matrix, which contains all of the unique elements, otherwise known as the sample moments. And then the model, once you've specified it, it also stipulates that a certain pattern of estimates would be contained in the variance covariance matrix. And that's a little technical, but I think that must make sense. You have an observed variance covariance matrix. You specify a model. The model stipulates or suggests that the variance covariance matrix would contain, the following entries. And then the goodness of fit asks, how well does the estimated matrix match the observed matrix? And because that's technical, and you can probably imagine there's a number of different ways to think about how you might try to ask the question of whether or not those match, or that the observed data fit the model. There's a whole bunch of goodness of fit statistics available. I mean, a whole bunch of them. They have a lot of subtleties in terms of what they might tell you and when you might use them in different situations. And so the next slides are kind of detailed information about each of the fit statistics. Because this is a really high level overview, I'll just say most CFA papers will report 3 to 5 fit statistics. And everyone reports a chi-square. So a chi-square, because you may recall even from intro stats, chi-square is in fact a statistic which reflects the deviation from an observed to an expected statistic. And so chi-square is sort of the gold standard of a fit statistic, but the problem is it's very, very sensitive to sample size. Because I think it is important to know about chi-square, as a deviation of observed and expected, what you want is the chi-square to be non-significant. You want the chi-square value that comes out of a model fitting endeavor to be non-significant, because that would say there isn't a significant difference between the observed and the expected. And that's why it is sort of considered the gold standard. But it's very easy to get a significant chi-square, even from a good fitting model, when the sample size is really large. So that's why it's most generally supplemented with a lot of other fit statistics. And I'm not going to spend a lot of time on each one. We're just going to sort of blaze through them, and then you'll have these slides for reference. Here's the chi-square. And it says that sort of down at the bottom bullet, despite the limitations of the chi-square, which are listed above, researchers generally will always cite this value. Another thing that's pretty commonly cited with respect to the chi-square of a CFA is to divide the chi-square through by its degrees of freedom and to look for a resultant statistic that's less than about 4, maybe less than about 3. So it should always be reported, and it should always be present in a CFA report. Oops, sorry, that's a duplicate slide. Then there's the CFI and the TLI. I list these next because they are most commonly the second reported ones. These are values which are scaled between 0 and 1, where higher values are better. So these are sort of like amped up correlation coefficients, and you want them to be really high. Okay, so the rest of these, as I said, I don't want to spend a lot of time on, except for RMSEA, which is probably, again, the next most common one. Just so you have some sense of familiarity with these when you see it. This is a statistic for which you want a very small value. The smaller, the better. Okay, so then this is the standardized root mean square residual. AIC is a really wonderful fit statistic, but can only be interpreted comparatively, so only to compare multiple models that are fit in the same data. Okay, so let's take a look at a couple of papers that I published over the last few years that are CFAs. So this is the multidimensional health locus of control scale, and this contains a confirmatory factor analysis of the scale, but it also contains invariance testing, which we're going to talk about next time. So there's really two things going on here, but I wanted us to be able to look in and think about the model. So here's the estimated model. All of the size, the latent variable covariances, the ETAs, the latent variable variances, all of the lambdas, which are the path coefficients, and then all of the observed variables. So there's 18 observed variables in this study. Is that right? 1, 2, 3. Right. So there's 6 indicators associated with each latent variable. So that's 18 total variables. So the sample moments available in this data are going to be 18 times 19 divided by 2. And that number, 18 times 19 divided by 2, is 171. And then we can look at all of the parameters that we're going to estimate in this model. So there are 3 latent variables, so you need 3 latent variable variances. There are 3 covariances. So there's 1 with 2, 1 with 3, and 2 with 3. That makes sense, right? So the covariance is among all of the latents. Then there are 18 lambdas, or path coefficients, minus 3, right? Because we lose 1 for every latent variable. So that's 18 minus 3 is 16. And then there are 18 error variances associated with all of the indicators. And so that number is 39. So if we take 171 sample moments available minus 39 parameter estimates, we get 132 degrees of freedom. And this is the results table from the paper. So well, it's a little hard to see. I'm sorry. The second entry, the second row, is the result of the 3-factor model. So you can sort of see over there, it says something 3 constrained model. But the parameters estimated are there, 39, which is what we just counted up. And you can see the degrees of freedom is what we just said, 132, which is 171 minus 39. The chi-square is very, very huge because this was a large sample. So the chi-square to degrees of freedom ratio is there, and it's 4.5, which is not great. And then you can see there's an AGFI, and there's some other fit statistics. So this paper is available to you if you want to take a look at it. So I would look at this model and I would say, it's not great. Even the chi-square to degrees of freedom fit or ratio is a little high, right? 4.5. I mean, it's not 14, but this is not a great fitting model. I'm sorry about that. So I just reproduced that table, but small enough so that the whole thing will fit on the screen. So we're again looking at that second row, model 1, which is the 3-factor model with 39 total parameter estimates and 132 degrees of freedom. So you can see same as before, just I made it so we could see it. The chi-square to degrees of freedom ratio is 4.5 and the RMSEA is 0.07, which is a little higher than we like to see. Generally, the cutoff is considered to be 0.05. We'll talk about this paper again next time when we talk about the invariance testing. So for now, all we're looking at is that middle row. And then here's another example of a confirmatory factor analysis that I did back at Jefferson with Dr. Hojat. And I've reproduced the figure here. So this scale has a similar structure as the one we just looked at, which is a 3 latent variable structure corresponding, in this case, to 20 individual indicators or scale items. And so the reason we're going through all of this, right, is so that we get really good at practicing parameter estimates and sample moments. This particular one I'm not going to do for you because I think you can do it. So I hope that the presentation gave you some familiarity with looking at these models, thinking about what they mean, counting parameter estimates, kind of understanding what goes into a results table. So you'll notice the results table for these models contains fit statistics. It doesn't contain parameter estimates. The parameter estimates usually would be reflected on a figure like this one. There are obviously a lot of other subtleties associated with these models. We know that if you look at the latent variable to indicator path coefficients, so start in this particular figure, starting at the top, it's 0.58, 0.46, 0.34. Those represent the loading of the item with its underlying latent variable. And the reason we don't represent the actual estimate associated with the error variance is because it's 1 minus that. So even though it has to be estimated from the data, it's pretty customary to not represent it in a figure. But you know that looking down those, right, if we're hypothesizing that this underlying latent variable, perspective taking, causes scores on each of these items, or these are the scale items, then we want those values, or we expect those values to be really high. This latent variable, we're saying, causes scores on the indicator. So we want those coefficients to be close to 1. So for cases where they're not, like item 5, where the item to latent variable loading is 0.34, we might say, oh, well, that's not great. The corresponding error variance for that item is going to be very high. And part of the subtlety around these models is, what do we do with that information? Because this is a confirmatory strategy, right? What we're trying to do is confirm that the items that we have fit the model that we hypothesize. And so if you fit a confirmatory model and it doesn't look great, the question is, well, what would you do then? And I think we talked about this a little bit in class. You know, if you're in a position to revise an instrument, this is a really powerful source of information for thinking about revising instrumentation. Is it, do you need to go back and remove some items? You can see there's another item here that is hypothesized to load on or go with the second latent variable, which is compassionate care, that has an item to latent variable loading of only 0.27. So that's very, very low. And then it happened in in the case of the Jefferson scale of empathy, which is what this is, that after all the items were written, you know, when the scale was developed, the items were written, they were refined. There was some cognitive interviewing that happened to make sure that people were doing the item, interpreting items the same. And then huge administrations in real samples started happening. And then a bunch of exploratory factor modeling happened. And the exploratory factor modeling, it emerged that one of the underlying latent variables only has 2 items associated with it. And that's that final one on the bottom, walking in the patient's shoes. So if you were going to develop a scale to begin with, it's not ideal to have an underlying latent variable that only has 2 items associated with it, to have an unbalanced scale like this. And so, but if you've already written the instrument and published it, or it's already in use, which is what happened with the Jefferson scale of empathy, it might at that point be too late to go back and say, oh, we're going to remove some items, we're going to maybe write some new items, we're going to rethink about the nature and scope of the conceptual space here. And so that's what you'll see happening very often, is that modestly well-fitting models are published because we're not in a position probably to revise the instrument. Okay, so that's the end of the lecture. Let me know if you want some more in-depth discussion of CFA. In the other specialized course in your track, which is PHS 710, you will actually learn how to fit and estimate these models in R. So I do hope that if you have an opportunity to take that class, that you will, if you're interested in this modeling approach. I'll see you guys soon.